Right, hello and welcome. Today is Monday, May 4th. May the Force be with you. Today we will go over our quiz from last week. It was a pretty big wake-up call, I hope, for most of you. Now, luckily, there are no multiple choice questions, but at least the concepts and the physics are still part of it, right? So we definitely need to pick it up. We have exactly 1 week, so a week from today, you're all doing your AP test, right? And APC is up first, so you guys are up first. What was it, 9 o'clock? I don't know, I forget. I gave you the times last time. Was it 9 o'clock? Yeah, I think it's 9 o'clock. Can someone verify in chat if it was 9 o'clock? Yeah, so let's see. It was 9. Okay. Oh, the APC test. APC test. Homework. Homework. 17, 18, 19, 20, 17, 20, 18, 20, 19, mechanics, FRQ, all of them, ENM, FRQ, 1 through 2. All right. So your homework, which is due this Saturday, which is the 9th. If anyone actually turns this stuff in on Saturday, I'm going to be mad. I'll just say it is due with air quotation marks. It is due on the 9th. I'm going to glitch Canvas, so so something goes wrong on Saturday. It is due on the 9th on Canvas. So similar to how you did your spring break stuff, or I should say crack AP stuff. Take pictures. Make sure you take pictures. I don't know if you read your comments. Try to make it nice and straight. Get some lighting, so that it's easy to see. And write dark, or I guess use a pen. I don't know. You don't have to use a pen. Just write dark, or if you're using a pencil, make sure it's easy to see, especially if you have bad lighting when you take pictures. So go through the College Board's released FRQs. See, these are the released FRQs. Oops, release. Released FRQs. So for mechanics, you're going to do all of them. There's 3. So each test has 3. So that's 9 from mechanics, 9 from mech, and we're only doing the first 2 for ENM, so that's 6 from ENM. All right. Let us begin. With our quiz. Oh man, there's a lot to learn today. I guess, unfortunately. Let's start with. I'll leave the electricity. I'll just do the mechanic stuff first. The mechanic stuff. Let's see, mechanic stuff. We'll begin with the cantilever question. This is a classic physics question, where you have a block that is leaning over the edge of a table. Right? And what you're trying to do is stack the blocks so that they can go over as far outwards as possible. Right? And you can keep doing it. Oh, I know, it said MC, but I made all the MCs fill-ins, and I just deleted all the choices, and I just turned the question into a fill-in. So you can't like check if the answer's there. You have to like do it and like, do it by yourself. Or there's no guess and check. There's no process of elimination. Right? Which is more practice for FRQ types, right? You can't really check answers in an FRQ question. You just got to do it. All right, so anyway, what we want to do is find D, the overhang. We actually had a physics club activity many moons ago. Well, of course, yeah, in 25 minutes. Well, the 25 minutes is a long question. Remember, there's a long question and a short question. So the first one is 25, and then the second one is 15. Which is fair, because most FRQ questions on the APC test are all 15 anyway. And multiple choice, technically multiple choice are 1 minute and 17 seconds, and this time I chose slightly harder questions, so you guys had technically 10 minutes to do five of these. So you had 2 minutes per question, which is more than what the College Board would have given you if there was a multiple choice section. All right, overhang distance. So what do we know about about this, about not falling over? We did something similar, right? If you remember, even in like AP1, each one is half. No, each one is not half. Even in AP1, is that in order to stay on the edge, you have to make sure the center of mass. So if I just did, let's just start with 1. If I just have 1, the center of mass of the object has to be directly at the edge. The edge serves as your pivot point, the fulcrum. So you're balancing the two sides of the masses on that fulcrum, right? So we want the center to be on the fulcrum, okay, such that the torques cancel each other out. Now, if you put a second mass on top of it, of course, it's going to put more torque on this side, therefore more likely to tip in. So what you could do is slide your mass slightly inwards so that the second one can move out. Now you can maximize the overhang of the second one by placing the second one such that the center of mass of the second one is at the edge of the first one. Right, so that's now we know that the second one is maximized. We just have to make sure that the first one is not too far out, otherwise the first one will tip over. So this is a purely center of mass type problem. We have clockwise and counterclockwise torque. Remember, this you want to treat it like an FRQ, so you have to go about doing the problems starting with FPDs and all sigma equations, and do all that to prove your thing, right? It's not enough just to tell me what it is. Although technically in your quiz it was enough, but on the and the AP test it will not be enough. All right, so here's our fulcrum. And what we could do is say that this distance here, just for the first one, is sub x amount, right? And of course, this thing would be half the distance, or half the thing of your length. Let's say this is length L, so this green part is L over 2. And so the overhang distance d is equal to the x plus L over 2. We just have to figure out what x is. Now to do that, we can do some torque stuff. Let's see. Notice how the center of mass of object 1 is some small distance away from the edge of object 1. How much is it? Well, it would be, this is L over 2 minus x. Okay. How did I get that? Well, we know that the center of mass is halfway, so this is L over 2. Okay. So x must be half minus whatever x is, right? So, all right. So now we just do torque and set them equal to each other. We have clockwise torque and counterclockwise torque. Since the fulcrum is the edge of the table, the green object, the center of mass of the green one, provides a clockwise torque, whereas the black one here provides the counterclockwise torque. Okay. So we'll set the two torques equal to each other. So we get mass 1, which is m, times gravity. Now we have the force. And force times the radial arm. The radial arm is whatever this thing is. L over 2 minus x. Okay, so mgr is equal to the clockwise torque, the green one. And the green one would be mass of the second object, which is m, times gravity times the radial distance for the second object, and that's just x. And then we solve for x. Mg's cancel, so we have L over 2 is equal to 2x. And so L over 4 is equal to x. All right, so x is L over 4. So d is equal to L over 4 plus L over 2. Remember, d is equal to x plus L over 2. All right. Uh-oh, baby's crying. Well, next one. What's the next one? Should we do the momentum one? Let's do the momentum one. I don't know if we're going to have time for all of them, actually. We'll try to get through as many as we can. The momentum one has an object that explodes. Of course, momentum during explosions is also conserved. Yikes. So here's an object that is moving to the right. Wait, what? One half plus 1/4 equals 3 halves. Ay, ay, ay. That is. You know what that is? Ooh, it's a great time to use our new emote. Oops. That is the integral of dl. We have our emote approved by Twitch, so feel free to use our new emote. Oops, I went to a different page. Okay, it explodes into two pieces. One part goes downward, straight down. One part goes at some angle. It's not 45 degrees, even though it looks like it. You can use your points to use the emote in my channel at least. The second object goes at some angle theta. Okay, this is just a classic two-dimensional momentum problem. They're giving you m1. They're giving you v1 initial. I'll call it v1i. What else do they give you? They give you... I'm going to call this m, not m1, sorry. M, comma. And they're giving you m1, which is the broken piece. I need to... I don't know how to actually change the values. So people can't spend. I mean, you could be like Ryan Davis, who just like stays here forever and just farms all the points. I did notice Sword Hero is not here today. All right, M1. They're giving you M1. They're also giving you V1 final, and then here you just know what M2 is. Okay, but anyway, momentum has to be conserved in all axes, x and y, right? So you have to do conservation of momentum twice and then solve. It's a pretty generic problem. Let's see, let's do px. So at px we have initially mass times velocity 1I. All of it is in the x-axis, so that's nice. At the end we have two. We just have m2, m2 v2 final x, where v2 final x is equal to v2 cosine of theta. V2 final cosine theta. We can also do y, momentum in the y-axis. This is momentum, so I'll use the vector hat. There we go. In the y-axis, we have 0 initially. Now this is conservation of mo. In the aftermath, we have both. So let's see. P2y. Mass to velocity to final y. Now, should I do minus or plus? Well, if I know that v1 final is a negative number, then it would be plus. If I just wanted to use magnitudes, then I would do minus. Typically, in a general problem, general equation, you would just write it as a plus. M1 V1 final. Okay, and then later on, you just have to keep track of if V1 final is a negative number or not. Okay, so we have M2 V2 final y is equal to negative M1 V1 final. Now, V2y, of course, is the same as V2 final sine of theta equals negative M1 V1 final. All right. So that's that. You can solve for V2fx. V2fx is M1 V1I divided by M2. Okay, which is equal to V2f times cosine of theta. Therefore, V2f V2F is equal to mv1i over m2 over cosine of theta, like so. And this will allow you to substitute and then solve. Right? You get a tangent and then arctan to get the theta. Okay, so that was the momentum question. Pretty straightforward. What's the other one? Ah, yes, the MIT style question. Here's a wall. There's a variant of the momentum question where instead of finding the angle, it has you find the actual velocity. Either way, it's done the same way. You're just solving for it. Either find the angle first and then plug it in, or whatever. All right, let's get to the MIT style question. The MIT style question: you have a wall, you have a pivot, a joint, and a beam. So here's our beam. That is hanging. At the edge, we have a hanging mass. Okay, and directly at the middle, we have a beam support right here that is holding it. All right, chat. Which direction, if I were to do an FPD for the beam, which direction is the force from this support here at the middle? Whoa, what direction is that force on the beam? The force on the beam by the support. Okay, remember this thing. So again, the beam is the green thing here. Let me color code. Here's the beam. It's green. On the edge here, we have a hanging mass. So of course, the hanging mass is trying to pull it down, pull the beam downwards. But this black thing is a support, so like a shelf support. Okay, and it is attached directly at the center of our beam. So if this thing is supporting it, which way would the applied force be? It is not up. The block is held by some sort of rope or something. It doesn't matter. Well, it is at an angle. It is at an angle. The support would be pushing it along the line of action, so at some angle this way. This is some sort of applied force. Well, what do we call this? Let's see if it's actually called something. Strut. Oh, this is the force of the strut. That's what it's called, a strut. I'll call it F strut. Okay. Now at the center, we also have the gravitational force, right? So we have M. I'll call this MB. B for beam. Whoa, this is an A. Massive beam. So MBG. And we also have the hanging mass, so that's mg. And finally, the pivot force. So what's going on at the pivot force? Well, the pivot force has to keep everything in static equilibrium. So assuming everything is perfect, notice how the strut is upwards to the right. So there's some sort of x component for our pivot force to the right, and so in order to stay in static equilibrium, there has to be a leftward force at the pivot. So the pivot force could be somewhere left or somewhere this way or something like that, depending on what the masses are and all that, right? All right, so there are two variants. One of the question is, what is the force? The x component of the force. It says find the magnitude of the x component of the force exerted on the beam by the pivot. This is the pivot force, FP. Okay, the x component must be, without knowing what the y component is, whether or not there is, it doesn't really matter. We know for a fact that there must be an x component equal to the x component of whatever this is. All right, so this one was pretty simple. It's just force of the strut times the cosine of the angle. Now, what is this angle? Well, they give you 4, 5, some lengths. So this is a 3, 4, 5 triangle, right? So you can use some trig to find the angle. Now, this angle that I use, theta, would be this angle here. So if I redraw my triangle, the hypotenuse is 5. The side length is 3. So theta is, and this is 4 here. I could do arc sine, I guess, or just arc cosine of 3/5 equals theta. Right. So that way, if it's fs cosine theta, then it's fs cosine of arc cosine of 3/5. All right, yada yada yada. So you missed the theta? Oh, come on. That is definitely, man, I keep doing it twice. I don't know why I do it twice. Fs. Isn't Fs basically a normal force? Fs is the strut force, meaning this is the strut. It's like the shelf it's a shelf support. And so if you're hanging on a shelf, the shelf is going to push you along the line at the point of contact. It's going to push you at an angle. That way. Just imagine, like, I mean, you're thinking that it's a normal force and it's 90 degrees. Well, no, that's not necessarily true. Think about it this way. Here's a door, right? Here's a door. And the door, and here's the axis of rotation for the door. And the door can swing around this axis, right? Now, technically, you can apply your force correctly, with into the page here. Let's do applied forces into the page. So if you apply your force into the page, well, not here, but on the door. There we go. Let's say you push the door. Yeah, the door is going to swing because now the radial arm is this way and the force is into the page, so the door swings inwards, right? But you don't have to push the door at an exactly 90 degrees to the radius vector. You could push on the door sideways. I mean, why would you do that? I don't know. Some people have small brains. But if you did, then the applied force, of course, would be at an angle, right? And only the y component of the force would be turning the door or opening the door, whereas the x component of the force would go into the hinge. That's Newton's shelf theorem. That's pretty good. That's pretty good. I need to create a new one. I need a wireless high five emote. That's the next one I'll make, probably on Wednesday or something. Let's see. Is that it? Oh, there's another one where you have to solve for mass. To solve for mass, do torque. So if you got the mass problem and you're trying to find the hanging mass, do torque. Now, if you're doing torque, you want to strategically choose your axis of rotation. Remember, you want to pick your axis of rotation so it cancels out forces, especially ones where you don't know what they are. Okay, so I'm going to choose the hinge or the pivot as the axis of rotation. That way I just have to worry about these three forces, the ones that I actually know. Yeah, we're not done. This is just the second variant of this mechanics problem. So not all the multiple choices are the same. So some of you got different questions. So one of the question was to find the x component. So the second variant is to find the actual mass. So with torque, let's see. To do torque, we have three forces, right? Based on the axis of rotation being all the way out to the left side here, we have two clockwise torques. So mg is pulling me clockwise, mbg is also pulling me clockwise, whereas the y component, the y component of fb is the other way. All right, so they'll do clockwise minus counterclockwise and then solve for mass. Let's see. Counterclockwise is fby times the distance from the axis of rotation, and the distance from the axis of rotation would be half the length, and it must equal the two clockwise added together. No, that's what we're trying to find. So the two clockwise would be m beam times gravity times the distance from the axis of rotation, and it's at the center of mass, therefore is also L over 2, plus the torque for the hanging mass, m, which is what we're trying to find. I'll use green here, green, m, times gravity times the full length, L, and then solve for m. ISO. All right. So that was it for mechanics. There was a couple of E&M questions, starting with the kinetic energy one. We have a proton and alpha particle. So here's a proton, P plus, and an alpha particle moving towards each other. Okay, it's pretty straightforward in that what we're doing is we're conserving energy, so our kinetic energy becomes potential energy. KE of the system becomes PE of the system. So the charge of a proton is 1e. The charge of an alpha particle, which is helium, is 2e. Remember, alpha particle is 2 protons and 2 neutrons. So you should know alpha, beta, gamma, right? Alpha is helium nucleus. Beta is a high-speed electron that was ejected from the nucleus during decay, and then gamma is, of course, light. How would we know that? What do you mean? You have a full chart of all the fundamental radiation and all the particles and stuff, right? We have a chart of stuff from alpha, beta, gamma, proton, neutron, electron, positron. What else do you have? I think that's it. That's all we have. And I mean, not only that, it actually tells you, right? What does it tell you? Where is it? An alpha particle is a nucleus of helium. I mean, you should definitely know what helium is. That's middle school science. You should know what hydrogen is 1 and helium is 2. So you should know it has 2 protons, and 2 protons is 2e. Can't make it any easier than that. So 1/2 times mass of the proton. Now both of them are moving at 0.0. Oh gosh. I mean, the first sentence tells you, the question starts with, an alpha particle is a nucleus of helium. 1/2 m1 1/2 m1 times velocity 1 squared plus 1/2 m2 velocity 2 squared is equal to potential energy of the system would be U or KQQ over R. And you're just solving for R. Yeah, they repel because they're both positive charges. So as they come closer together, they'll start repelling. Imagine the repulsion being a spring, right? And so as these two come closer and closer together, you're compressing the spring. And this is a theoretical electrical potential energy spring. My physical science teacher made us watch a show called Cool Japan during class. We wasn't worried about nucleus of what? Cool Japan. What is the show about? Does it have anything to do with science? Like basic chemistry, like you don't have to take AP chemistry to know that helium is 2. This is part of like middle school science curriculum to know the basic elements and stuff. It's about how Japan is cool. And they have obento boxes, lunch boxes, where they have like these little sandwiches where they cut the crusts off. Ah yes, the best sandwich. And they always make this red bean paste stuff. They love that red bean paste thing. You think we learn in middle school? What do you mean? Don't be rude. Yes, you learn. Like Hale gets like so much money. They have like all these 3D printers and stuff. So they're learning a lot. All right. Let us see. What else is left? Did we cover everything? I think we covered everything. Oh, there's one question. Ooh, this one was mean. I'll be honest. This one's tough. It was the electric field question, where you have a conductor of uniform charge density, and a lot of you went straight into thinking it's a plane of charge. And, this one is definitely mean. So let's pay attention. So if I had an actual plane of charge, we found that the E is equal to eta over 2 epsilon naught, right? Now what is different is that they didn't say, it was a very small word that was very rude and mean. They didn't say, your some distance, some 3 millimeters of distance above a very large sheet. They didn't say find the electric field at some point above a plane of blah blah blah. That's not what they said. What they specifically said was find the electric field outside a conductor. Yeah, I definitely chose the hardest problems I could find. So not gonna lie. And so you're trying to find the electric field outside a conductor. So what can you do? Well, technically you can actually treat any conductor kind of like a ball. And so if you're outside a sphere of charge Q, or whatever the density is, of course this is linear density eta, so all the charges are all spread around the conductor. And so anytime you're outside of a conductor, the electric field is equal to eta over single epsilon naught, not half. So some of you got, some of you used the plane and your answer was half of it, but it has to be twice as much. Now, why is it treated like this? Right. So first of all, you have to know that any point outside of a circular charge conductor, whatever, is equal to, you have to know this part. Now, how do you get that? You can use Gauss's law, of course, Q enclosed over epsilon naught, and solve for it. And Newton's, Newton's theorem, shell theorem, will help you get there as well. Now, let's take a look at how these two are the same. So if I had, instead of doing a full pill, instead of using a sheet, let's say I just use partial. Gauss's law has to work no matter what your Gaussian surface is. That's the beauty of it. And let's go dig downwards. Imagine, instead of being just a plane, this is applicable to any shape, really, as long as you're outside of that shape, outside of the conducting material. Let's say you have a really weird shape, and you can still have eta being the surface charge density, plus, all scattered around the surface. Okay, and so I'm going to just find the electric field here. And so in order to do that, let's create a Gaussian surface like so. So for these weird abstract shapes, you can still do partial and still figure out what it is using partial, this Gaussian cylinder here. Okay. Now, since the charges are all on the surface here, the electric field points this way, right? And the area vector for this circle also points in that direction, so you get 100% flux, therefore you get some electric field. Okay, now what about the side of the cylinder? Well, the area vector for the side of the cylinder, is always orthogonal, or 90 degrees to the surface. But the electric field, remember, is away from the positive charges, so the electric field would be 90 degrees now. And recall that it is a dot product, the flux. So since it's a dot product, the dot product of 90 degrees would give you 0. So therefore nothing exists on the sides of your cylinder. Now, what about the inside? I'll use a different color. Okay, you're inside a conductor. What is the electric field on the inside of a conductor? Chat, what is the electric field on the inside of a conductor? Whether it's a sphere or this weird bean-shaped thing. It is 0, good. Why is it 0? Well, because of symmetry and all sorts of cool stuff that happen. Right? So things that push away, and then all of these would point towards, but they're further away, so all the vectors kind of cancel each other out. Okay, so you can see how if I did Gauss's law, you get E times area, just a single area. Recall that if I take the integral, E dot dA gives me E times integral of dA, which is E times A. This time it's just E times A. It's not E times 2A, because the green one is 0, is equal to Q enclosed, whatever the Q enclosed is, divided by epsilon naught. And so we have E times Q enclosed over A times epsilon naught, and this is just eta. So again, as long as you're outside of a conductor, it is epsilon over eta over single epsilon naught. And so similarly, this conductor would also have 0 here inside. Yeah, we are now inside of the object. Can you explain the required symmetry for Gaussian surfaces? I mean, to make the integrals easy, you choose surfaces that are symmetric to the object itself. But the thing is, it doesn't have to be symmetric to the shape. You can use, like, even though I have a weird, potato-shaped surface or object, I can still use Gaussian cylinder to do it partially, and it'll still work, right? Why does this work? That's because let's take a look. Notice how when I encapsulate the charge, the Q enclosed is only based on these charges here. These ones that are inside on this circle on the surface. So notice how I have less charge, but eta is uniform dense. Eta is still going to be charge per area. So of course I'm going to have less charge, but my area is smaller. It's a tiny little circle, not the full area. So even though I'm not using Q total, but since eta is constant, whatever Q I'm using is going to be in proportion to Q total over A total. Right? The entire surface, the entire charge divided by the entire surface area is also equal to the tiny little amount of charge that I'm encapsulating divided by the tiny little area. And so that's why the Gauss's law works. Even though my shape is very complex, I don't have to have a complex Gaussian surface. I can just use a simple Gaussian surface. All right. Yeah, like I said, that was definitely the hardest question, and I chose that just so we can differentiate the difference between finding the electric field at a point above a plane of charge versus finding the electric field outside of a conducting object. Whether it's a circle, it's a potato, or it's a plane of sheet. So based on how they word it, it is what it is. All right. Finally, the capacitor stuff. The capacitor stuff, I think, obviously, because it's a essay type question, it's blank out of 15 right now. So currently, whatever score you see is the maximum would be 15. And then once I add in the FRQ essay question, then you'll get a new score out of 30. I can at least go over some of the concepts because we are running out of time. So here's the circuit. We have a switch. We have two capacitors, a resistor. The first one is charged up, and the second one is not charged, and we have resistor R. A, calculate the charge Q on C before you close the switch. So it was stated that C1 is initially charged by a 30-volt battery. C1 initially charged via 30-volt battery. So before plugging it into the circuit, we charged up our capacitor with a 30-volt battery, and then we plugged it in. Right? So this charged capacitor is going to act like a battery once it's in our circuit as it discharges. That's the idea, at least. Okay, so I mean, step A, find Q. Well, Q is equal to CV. That's pretty plug and chug. Multiply the capacitance, which is given, times the voltage, 30. And that is all. All right, part B. What is part B? Part B says the switch is now closed. Okay, we close the switch. Pew. So now the charged up capacitor starts to discharge. Part B says let Q2 be the charge on capacitor C2. So this is Q2. So the original Q here is capital Q. What? Why can't I write? That's so weird. Q. All right. So as a function of time, as time goes on, Q2 is being charged up as Q is dissipating or discharging. Can you explain the requirement? I thought the surface had to be the same on each side of the charge. It is. What? It is. Look. my pink A is the same as my green A. My Gaussian surface is the same on both sides. But the electric field inside is 0, so there's 0 flux for the green one, whereas the electric field outside is away in the same direction as A, so the flux is 100%. All right, so how do we do B? Okay, so we want to find Q as a function of time. It says write but do not solve. So here it is. You don't actually have to solve the differential equation. You just have to write it. A differential equation is basically something with like a dx dt or something. That's what a differential equation is. It's something that has, you know, d of some variable over d of some other variable. Usually, you know, dt. So if you do like a dx dt or a dq dt in this case, that would qualify as a differential equation. So first we have to do a loop rule, right, to figure that out. So V1, which is the capacitor of voltage in capacitor 1, minus the V2 minus the voltage in the resistor is equal to 0. There's our loop rule. Okay, then we plug in some stuff. Let's see. The voltage of capacitor 1 should be the charge of capacitor 1, Q1, divided by C1. Recall that for capacitors, Q equals CV. That's the general formula. Voltage. So Q divided by C is the voltage, minus Q2 over C2 minus current times the resistance R is equal to 0. Notice how I use little q1 instead of capital Q. Chat, what is capital Q? What is this capital Q here that we solved for in part A? Total charge. Good job. So capital Q is the total charge. Q1 is a function of time. Remember, Q1 is the current charge in capacitor 1. Okay, so we could actually rewrite this. The current charge in capacitor 1 is actually the total charge minus the charge in capacitor 2. Whatever went into the second capacitor is the charge that you lost from the first capacitor, divided by C1 minus Q2. And I want to do this so that I don't have too many variables. I only have one variable, and I can actually is equal to, oops, I keep saying equal to, minus IR equals 0. And all we have to do, remember, we're not actually trying to solve anything. We're just trying to write this as a differential equation, meaning somewhere here I need to be able to rewrite some variable as, you know, d something over dt, or, you know, of course the answer is to rewrite current. So if I rewrite current as a derivative, then I have created a differential equation. That's how easy this question is. Of course, the hard part is to figure out what the charge is. So if I move this term over to the right side, we can write dq dt. Yeah, I is equal to dq dt. Which q? I'm going to write dq2 dt times r. Or I could divide by r. Let's go and divide by r on both sides. dq dt is equal to q minus q2 over rc1 minus q2 over rc2. Technically, you're done. You wrote a differential equation. Now, of course, to make it elegant and actually solvable, you would want to kind of simplify things and all that. So you could rewrite this as, let's see, what can we factor out? We can factor out, let's see, q over, whoa, Since both of them have Q2, let's keep Q2 over here. You could do this, split the fraction, and then write it. Oops, 1 over. So you could split the fraction and do this. I don't know. But anyway, as soon as you do this and you have dq dt, you're pretty much done. You have a differential equation. All right, part C. What does part C say? Part C says, calculate the final charge Q1 and Q2 after equilibrium is reached. Okay, so we're going to reach equilibrium, so eventually everything dies down. When you reach equilibrium, no current is actually flowing in the circuit. All right, for using conservation of charge, remember the total charge, so Q1 plus Q2 at any point in time, right? Oh, whoops, I'm using capital here. I used lowercase on the previous example. So let's stay consistent. Actually, let's stay consistent with the problem, because they're labeling the charges now. Originally you had a choice, but now you don't. So they're saying that Q1 is the charge as a function of time of capacitor 1. And we have capacitor. This has to equal the original thing that you found in part A, the total charge at any point. Okay. And the voltage has to be the same. V must equal Q1 over C1, and it's equal to Q2 over C2. Remember, this is after we reach equilibrium. Therefore, the resistor is basically doing nothing because there's no current in the system, right? After we reach equilibrium, you could see that how capacitor 2 is basically parallel to capacitor 1, which is acting like the battery. Therefore, whatever voltage I have on capacitor 1 has to be equal to the voltage in capacitor 2. Okay. And then we can just solve. So Q minus Q2 over C1 has to equal Q2 over C2. And then you can solve for Q2 and Q1. I know, right? So when you see something like this, technically you can say that they are parallel or series. Doesn't really matter. It doesn't matter because whatever voltage you gain here, notice how you're going to lose it here. So whether you say it is series or parallel does not matter in this scenario. The answer is actually both, and you can argue both sides. The reason why we can say it's parallel is because the potential difference between the 2 points, let's call this point A and point B. Notice how this entire region is a nodal point. And the entire region here is also a nodal point. Therefore, the potential at these 2 points are the same. So the voltage gain is the voltage drop, etc. So you can, like, either way you want to look at it. V1 has to equal V2 because the resistor is not doing anything. All right, and is it the last part? Oh my gosh, we're going ham today. We're going overtime. Sorry, I shouldn't have used that term. What's the last? Oh, part D. Calculate the energy dissipated in the circuit as the charge is redistributed. All right, energy. Energy is, so whatever energy I have, the change in my energy should be energy final minus the energy initial. So, and the energy of a capacitor, I mean, this is the honors level almost at this point. They know the formula for capacitors, for energy of a capacitor. 1/2 CV squared. 1/2 C. So final energy is based on the energy of both capacitors. So let me use different colors. Here's UF, orange. So this would be final energy, which is 1/2 energy of the first one, Q1 squared, divided by C1. There we go. So Q, oops, I should write Q equals CV. Energy is equal to 1/2 CV squared. V is equal to Q over C. So 1/2 C times Q squared over C squared, which gives me 1 over Q squared over C. There you go. I wanted to use this because, V is not a given value and blah, blah, blah. Unless, you could solve for it technically if you solve for it, and then you can use V. Plus 1/2 charge of the second one squared over the second capacitance. Minus the initial energy. Initial energy is purely based on the first capacitor being charged, which is 1/2 Q Q, just Q, I'm going to use just Q, Q squared over C1. There we go. Okay, so that should give you the change in energy, and that's what you lost in the resistor. All right, part E was a gimme. Part E says what happens if R is increased, right? So R goes up, and a lot of you got this one. Tau goes up, so it takes longer. The time constant goes up. All right, that should be it. We're gonna have more quizzes. Should we have more quizzes? Should we do another tomorrow? Yeah, let's do quiz tomorrow. Quiz tomorrow. Quiz Thursday. And then on Friday we'll go over them. Why? You should time yourself, just like this is how you would do on the AP test. Time yourself. So give yourself 1 minute and 17 seconds when you're answering the multiple choice. If you can't get it, move on. Unless you're running out of time, right? You have to figure out how you want to spend the time. And it'll be technically easier on the MC, on the AP at least. But this is how we're going to do our final at least. So on the AP it'll be 2 FRQs. Yeah, you can't go back. Yeah, that is definitely the hardest part. I'm going to end the stream and then I'll hang on to Q&A. We can discuss this. Thanks for tuning in. I'll see you next time. Do your homework. See ya.